All right, I'm going to walk you through the answers to the Chapter 9 worksheet that's posted on Blackboard, and it's embedded into the SoftChalk module, the second one for Chapter 9. When you're given a problem like this where you have to predict the products, the first thing you need to do is look at what functional group you are starting with. And so we are given an alcohol, and specifically it's a secondary alcohol. Then you should kind of be thinking back through your head about what reactions you know that alcohols can undergo, and then take a look at the conditions that you're given. So it's being subjected to tosyl chloride. And if you remember, tosyl chloride looks like this. And this is where the oxygen comes in and attacks the sulfur, and you end up through a couple of steps eliminating that chlorine, and you get an oxygen-sulfur bond, and then we call that a tosylate. The pyridine is in there as the base. It's going to end up deprotonating here. So the bottom line is that since, first of all, at this chiral carbon, nothing happens, so we can leave that alone. And then also notice that this oxygen was doing the attacking, so nothing changed about the stereochemistry here. So we should draw this still the same way. And I'm just going to put OTS as the abbreviated tosylate. All right, once again, we have a secondary alcohol, and now we are subjecting it to H2SO4 in the presence of heat. H2SO4 is an acid who has a non-nucleophilic conjugate base. And so these types of acids are used to drive elimination reactions. So this is going to be a dehydration. And now we need to think about the mechanism. Does it go through a carbocation or no? And the answer is yes, it does. It's going to go through a carbocation. So then you have to think about rearrangements. So let's draw what the carbocation is going to look like. Here it is. There's really no way that this could rearrange. On this side, we just have hydrogens. Even if it moves over to here, that's only going to make it secondary. Of course, if it moves to this side, which it could, but it's not going to, this would be primary. So it's already at a secondary, it's going to stay put. So we don't have to worry about rearrangements. So now that we've decided the carbocation is forming right here, we need to identify the beta protons, the beta positions. So there's some here and here. If you take a look at if, let's say that it deprotonates on this side, we're going to get this product. If it deprotonates on the other side, we're going to have a more substituted product. Of course, you could potentially have cis or trans isomers, but based on Zaitsev's rule, we know you're going to get the more highly substituted product, and then we know of the two disubstituted alkenes that the trans is the most stable. So this is going to be the major product. Okay, let's do another secondary alcohol. And this time we're putting it in with PBr3. This is a brominating agent. And this is the one where the bromine will come in and attack. Recall that there's this new leaving group that's put on here. I think it's actually in this form. And the bromine, Br minus, is going to come in via an SN2 type reaction. And so in the end, you're going to have a brominated product, but the configuration at this carbon, notice that the bromine came in from the opposite side, that leaving group came off. Let's do another one, a secondary carbon. Notice most of these are secondary carbons because they're the most complicated. The secondary alcohols are always going to be the most complicated. So if you have a secondary alcohol and you subject it to tosic acid, once again, this has a non-nucleophilic conjugate base. So this is driving dehydration. And the heat there is another indicator that this is an elimination reaction. So we have to think carbocation or no. and it does have a carbocation that's going to form. So now we have to think about rearrangements if they're possible. The carbocation is going to form here, and right next door you have two methyl groups. So one of those is going to jump over, and we're going to end up getting the carbocation at the more stable tertiary position as opposed to the secondary position. Whoops, I put that on the wrong spot here. In the second part of this reaction, there's a beta proton removal. Now you have, once you've established where the carbocation is going to be, you need to identify the beta positions. If it eliminates from this side, and notice I'm not showing the stereochemistry of this carbon, I'll talk about that in a minute, but this is going to be the product from eliminating here. If it eliminates from this side, this is going to be the product. The question that you're being asked to answer is the major product. And so the more substituted alkene is going to be the major product. So we don't really need to even worry about the stereochemistry here because we're not asked to show those products. However, if it would have if the question would have said draw all products and indicate major and minor, then we would need to show the stereochemistry here, and we'd actually have a mixture of both possible configurations. Once again, on this problem, we have a secondary alcohol, but this time we're treating it with sodium hydride and then following that with treatment of an alkyl halide. When you treat an alcohol with sodium hydride, this is to deprotonate that oxygen. And so it doesn't do anything in terms of stereochemistry to this carbon here, that stays the same. The oxygen is now going to act like a nucleophile and come over and attack the alkyl halide. So you end up with an ether, and this is the Williamson ether synthesis. Again, another secondary alcohol. This time we're treating with HBr. This one does have a nucleophilic conjugate base, so this is used for substitution. And it's going to be a bromine substituting for an OH group. It does go through a carbocation, so we're going to need to consider that. Let's take a look at what this would look like. If the carbocation is here, you have a hydrogen that can come on over, and that's going to leave the positive charge here. Now we have a trigonal planar carbon that can be attacked in the second step from either face, and so we're going to end up with a mixture of Br up, methyl down, or Br down, methyl up. These are the products. Here we have a secondary alcohol. We're treating it with POCl3 and pyridine, and this is the method of dehydration that does not go through a carbocation. So we don't have to worry about rearrangements. We can go ahead and identify the beta positions, and notice that there are no protons here. So it can only eliminate down here. So this actually becomes a rather simple answer. We don't have to worry about the anti-periplanar stuff here because it's going to have a proton in the transposition that can be eliminated. So in the end, we're just going to have this product with the two methyl groups up here, and that's it. Okay, now we have an epoxide, which is a little different. When you see epoxides, what we do with these, we always are going to open them. And we can either open them in stronger, normally basic conditions, or weaker, normally acidic conditions. This is these are the weaker conditions, the acidic conditions. And in this case, the nucleophile is the ethanol. Tosic acid is the proton donor. And in the weak conditions, the nucleophile will attack from the more substituted side of the epoxide, and it does come into the opposite side of the oxygen. And so if we were to draw out what this looks like, 4 or 5, recall that this is getting protonated, and this is just going to open up. So when I draw this oxygen in, it's here. The methyl group, we're going to flip up. So now it is going to be sticking up, and then the nucleophile, which was the ethanol, is going to be coming down from the opposite way that ether was bridged.